the universe is roughly 13.8 billion years old. That is the number every textbook prints, the number woven into every cosmological calculation, the foundation of our entire picture of how the cosmos began and evolved. And until very recently, the evidence for that number was overwhelming. Multiple independent measurements, from the afterglow of the Big Bang to the distances of exploding stars, all converged on the same answer. Then, in July of 2022, the James Webb Space Telescope released its first deep-field images, and the objects it found in the early universe do not behave the way 13.8 billion years allows, not in some minor statistical sense, not in a way that might disappear with a better measurement. Galaxies have been detected in the early universe that appear to be fully formed, packed with billions of stars, chemically mature, and in some cases comparable in mass to our own Milky Way, all at a time when the universe was only a few 100 million years old. The physics required to build those galaxies in the time available, according to our best models, does not work. The math simply does not add up. This is not a fringe controversy. It is not the work of outsiders challenging mainstream science from the margins. These concerns appear in peer-reviewed astrophysics journals. They are discussed at the most prestigious conferences in the field. Nobel Prize-winning physicists have publicly stated that what Webb is revealing may represent a fundamental problem for our current understanding of the cosmos. Roger Penrose, who received the Nobel Prize in Physics in 2020 for his foundational work on black holes, has long argued that the universe has a history stretching beyond what our standard model describes. Others have gone further, suggesting that what Webb is seeing is, in the words of one prominent cosmologist, like looking at another universe. To understand what is actually at stake, you need to understand what our best model predicted, why those predictions were so well trusted, and why the discrepancies Webb has uncovered are genuinely difficult to explain away. The dominant framework in cosmology is called Lambda-CDM. The name comes from two components we cannot see. Lambda is the symbol Albert Einstein introduced as the cosmological constant, now interpreted as representing dark energy, the poorly understood force driving the accelerating expansion of the universe. CDM stands for cold dark matter, a hypothetical form of matter that has gravitational influence but does not interact with light. These two invisible ingredients dominate the universe's total energy content. Dark energy accounts for roughly 68% of everything. Dark matter accounts for roughly 27%. All the ordinary matter in the universe, every atom in every star and planet and living cell, accounts for only about 5%. Within this framework, the history of the universe follows a specific sequence. Approximately 13.8 billion years ago, the observable universe emerged from an extraordinarily hot, dense state and began expanding. For the first few 100,000 years, matter and energy were so thoroughly mixed that the universe was opaque, a dense hot fog from which light could not escape. When the universe cooled to around 3,000 degrees Kelvin, roughly 380,000 years after the Big Bang, electrons and protons combined to form neutral hydrogen for the first time. The universe became transparent. The photons that had been trapped in the hot fog streamed freely in all directions. We detect those photons today as the cosmic microwave background radiation, a faint glow filling the entire sky at a temperature of approximately 2.7 degrees Kelvin, cooled by billions of years of cosmic expansion. After that moment of transparency came a long, dark age. There were no stars, no galaxies, no sources of light, just an expanding ocean of hydrogen and helium gas, very slightly lumpy due to quantum fluctuations frozen into the fabric of space during an earlier period of rapid expansion. Gravity slowly amplified those lumps. Over hundreds of millions of years, gas fell into the denser regions, cooled, and began to fragment into the first stars. Those first stars were probably unlike anything in the present-day universe. Formed from pristine gas with no heavy elements at all, they could grow to masses hundreds of times that of the Sun. They burned intensely and died quickly, seeding the surrounding gas with carbon, oxygen, silicon, and iron for the first time in cosmic history. Their deaths created the first heavy elements. Their radiation began to ionize the surrounding hydrogen, gradually burning away the neutral fog in a process called reionization. The universe transitioned from dark and opaque to bright and transparent over a period spanning roughly from 100 million to 800 million years after the Big Bang. After reionization, the first galaxies assembled. Small structures formed first, then merged into larger ones over billions of years. This hierarchical bottom-up assembly is a core prediction of the Lambda-CDM model. The early universe should have been populated by small, dim, primitive proto-galaxies. Large, massive, chemically enriched galaxies like the Milky Way took billions of years to build. For a long time, observations appeared to support this picture. Every telescope we pointed at the early universe showed a world that was more primitive and less structured than the present. The farther back we looked, the closer the universe seemed to match what the models predicted. James Webb has now looked further back than any instrument in history, and what it finds does not match. The problem begins with mass. In the Lambda-CDM model, there simply was not enough time in the first few 100 million years for gravity to assemble galaxies comparable to the Milky Way. Building a galaxy of that mass requires accumulating gas, triggering star formation, allowing those stars to live and die and recycle their material back into new stellar generations, and repeating that cycle many times over. It is a slow process with hard physical speed limits. The universe was barely 2 to 3% of its current age when some of the galaxies Webb has found must already have existed. One study published in the Astrophysical Journal reported the detection of 87 candidate galaxies that may have existed only 200 to 400 million years after the Big Bang. Some of these objects are comparable in mass to the Milky Way. The Lambda-CDM model says they should not have had time to form, and yet the data indicates they are there. The mass problem becomes sharper when you consider star formation efficiency. In galaxies like the Milky Way today, only around 10% of available gas gets converted into stars. The rest remains as diffuse interstellar gas, or gets blown out of star-forming regions by the radiation and supernova explosions of the stars that do form. That 10% efficiency is not an arbitrary number. It is a consequence of real physical processes. When gas collapses to form a star, that star immediately begins emitting enormous amounts of ultraviolet radiation that heats and ionizes surrounding gas, preventing further collapse. Eventually, the star explodes as a supernova, sending shockwaves through the surrounding interstellar medium that disperse remaining gas and temporarily halt further star formation. This feedback loop is built into the physics of stars. It limits how efficiently gas can be converted to stars, and it is faithfully reproduced in our theoretical models because the physics is well understood. Some of the early galaxies Webb has observed appear to have converted nearly all of their available gas into stars. Not 10%, something closer to 100%. Spectroscopic analysis, which involves spreading a galaxy's light into its component wavelengths and reading the chemical fingerprints embedded in that spectrum, reveals whether a galaxy still contains significant amounts of gas. If it does, the spectrum shows it. The early galaxies Webb has been studying often show spectra indicating that the gas is largely gone, converted to stars at an efficiency our models say is physically impossible. A galaxy that achieved 100% star formation efficiency would have had to suppress the feedback mechanisms that limit star formation simultaneously across its entire volume at exactly the right moment. There is no known physical mechanism for that. It is not simply an engineering challenge. It is a violation of the physics our models depend on. So what are these objects? Several possibilities are being taken seriously, and none of them are comfortable. The first is that the Lambda-CDM model is incomplete. Dark matter may behave differently in the early universe than our models assume. The processes governing star formation in that primordial environment may have operated under different rules. The model may simply be missing something important about how structure forms in the universe's first few 100 million years. If this is the case, Webb is telling us that our theoretical framework, however successful in other domains, is not adequate for the early cosmos. The second possibility is that some of these objects are not galaxies in the conventional sense. Some fraction of the anomalously bright, apparently massive objects Webb sees could be dominated by active galactic nuclei, extremely luminous cores powered by accreting supermassive black holes. If the light from these objects comes mostly from black hole accretion rather than from stars, their apparent stellar masses could be overestimated. But spectroscopic follow-up observations have made this explanation increasingly difficult to sustain for all of the anomalous objects. Many of them show spectral characteristics that are consistent with stellar populations, not quasar cores. Some of them really do appear to be made of stars. A third possibility, raised seriously by several physicists, is that the universe is older than we think. Not slightly older, potentially much older. If the Big Bang was not the actual beginning of the universe, but rather a phase transition in a universe that had already existed for a longer prior history, then the early structures Webb is seeing might not be as impossibly young as our timeline requires. They might have had far more time to form. This idea connects to a broader class of theoretical models that challenge the standard Big Bang narrative. Some propose a cyclic universe, one that has passed through many expansions and contractions, with our current epoch being just one cycle among many. Others propose that the Big Bang was a local or regional event in a much larger and longer-lived cosmos, rather than a universal beginning. Roger Penrose's model, called conformal cyclic cosmology, proposes that our universe is one in an infinite sequence of cosmic aeons. At the end of each aeon, when all massive particles have decayed and only massless radiation remains, the universe loses its sense of scale, and a new Big Bang becomes the start of the next aeon. Penrose has argued that this model might be testable through specific patterns in the cosmic microwave background, and the search for those patterns is ongoing. These are not mainstream positions in cosmology. The Lambda-CDM model remains the best supported theoretical framework we have. But the fact that serious, accomplished physicists are raising these alternatives in peer-reviewed contexts says something important about how significant the Webb observations are. To appreciate what Webb is actually showing us, it helps to understand the remarkable physics that allows us to see the early universe at all. When you look at a distant galaxy through a telescope, you are not seeing it as it exists today. You are seeing it as it existed when the light you are detecting was first emitted. Light travels at just under 300,000 kilometers per second, which sounds incredibly fast until you consider how vast the universe is. Light from the moon takes about 1.25 seconds to reach us. Light from the sun takes approximately 8 minutes. Light from the nearest star beyond our own takes just over 4 years. And the galaxies Webb studies are billions of light years away. When Webb observes a galaxy that existed only 300 million years after the Big Bang, it is detecting light that has been traveling for approximately 13.5 billion years. That light is a fossil, a snapshot of a universe that no longer exists in that form, preserved in ancient photons that have crossed virtually the entire history of the cosmos to reach us. The expansion of space adds another layer of complexity. As light travels through the universe, the space it is crossing continues to expand. This stretches the light's wavelength over the course of the journey. A photon emitted in the ultraviolet by a galaxy in the early universe arrives at our detectors with its wavelength stretched by a factor of 10 to 15, placing it firmly in the infrared. The amount of this stretching, called redshift, tells astronomers how much space expanded during the photon's journey. From that, they can calculate both when the light was emitted and how far the source was at that moment. This is one of the most elegant tools in observational astronomy, and it is why an infrared telescope like Webb is essential for studying the early universe. The most distant earliest galaxies have had their light stretched far beyond the visible range. To see them, you need detectors that operate in the infrared. Previous infrared space telescopes lacked either the mirror size, the detector sensitivity, or both to detect individual galaxies at the distances Webb routinely observes. Webb's mirror, at 6.5 meters across with 18 hexagonal segments, has more than 6 times the light collecting area of the Hubble Space Telescope in the relevant wavelength ranges. But collecting more light is only part of what makes Webb exceptional. To use its infrared capabilities effectively, the telescope must be kept extremely cold, because any warm object emits thermal infrared radiation that would overwhelm the faint signals from distant galaxies. Webb operates at temperatures below 50 degrees Kelvin, roughly negative 223 degrees Celsius. To achieve this, it carries a 5-layer sun shield, roughly the size of a tennis court, which keeps the telescope in permanent shadow, shielded from both the sun and Earth simultaneously. The engineering required to deploy this structure in space, unfold it correctly, and maintain those temperatures for years, at a distance of 1.5 million kilometers, from Earth at the gravitational balance point called the second Lagrange point, is an extraordinary technical achievement. Webb carries 4 main scientific instruments. The near-infrared camera, responsible for most of Webb's iconic deep-field images, captures light across wavelengths from about 0.6 to 5 micrometers. It is the instrument that produced the first full-color image released in July of 2022. which showed thousands of galaxies in a tiny patch of sky. The near-infrared spectrograph can simultaneously capture spectra of up to approximately 100 objects at once, using arrays of individually controllable microscopic shutters to select specific targets in its field of view. This instrument has confirmed the distances and ages of many of the early galaxy candidates Webb has found. The mid-infrared instrument covers wavelengths from 5 to 28.5 micrometers, enabling detection of dust-obscured star formation that optical and near-infrared observations would miss entirely. And the fine guidance sensor and near-infrared imager and slitless spectrograph serves both a navigation function and scientific purposes, including time series photometry for studying variable sources. Together, these instruments give Webb capabilities that are qualitatively different from anything that existed before. This is why the scientific community was, in some ways, unprepared for what it would find. Predictions for Webb's early universe discoveries were extrapolated from what Hubble and earlier infrared telescopes had seen. Those extrapolations significantly underestimated the richness and the anomaly of what was actually out there. One of the most distant individual objects Webb has confirmed is the galaxy designated JWST Z14-0. Its redshift places it at approximately 13.5 billion light-years from Earth in look-back time, meaning the light we detect was emitted when the universe was only about 290 million years old. That is a staggeringly short time after the Big Bang for a fully formed luminous galaxy to exist. And yet there it is, captured in Webb's infrared detectors. That galaxy is not sitting still in space. The universe has continued expanding in the 13.5 billion years since its light was emitted. Today, JWST Z14-0 is estimated to be more than 30 billion light-years away from us, well beyond the edge of the observable universe. Any light it emits today will never reach us. Space is expanding between us, and it faster than light can cross the growing distance. Whatever that galaxy has become over the past 13 billion years, we will never know. We are left with a single ancient snapshot, and that snapshot alone is already telling us something our models cannot explain. This leads to one of the most counterintuitive features of modern cosmology. The observable universe is not the whole universe. It is simply the region from which light has had time to reach us since the beginning of our cosmic epoch. The observable universe forms a sphere roughly 92 billion light-years across, centered wherever you happen to be standing. Beyond its edge, space continues. Galaxies exist, stars burn, but their light will never reach us, because the universe's expansion carries them away faster than light can close the distance. As you look toward the boundary of the observable universe, you are looking further and further back in time until you reach the cosmic microwave background. That faint afterglow from 380,000 years after the Big Bang is the farthest thing we can ever observe. Before that moment, the universe was opaque. No light escapes from before that time. The cosmic microwave background has been mapped with extraordinary precision. It fills the entire sky at a nearly uniform temperature of approximately 2.7 degrees Kelvin, but it carries tiny temperature fluctuations on the order of 1 part in 100,000. These fluctuations represent the seeds of all the structure in the present-day universe. They have been measured by missions including the Wilkinson Microwave Anisotropy Probe and the Planck satellite. The patterns in those fluctuations match the predictions of the Lambda-CDM model with remarkable precision, better than 1% for most parameters. This is exactly what makes the Webb observations so puzzling. The Lambda-CDM model is not a bad theory. It is an extraordinarily successful theory. It explains the cosmic microwave background, the abundance of light elements formed in the first few minutes after the Big Bang, the large-scale distribution of galaxies across billions of light-years, and the accelerating expansion of the universe. It fits virtually everything we have carefully measured about the cosmos. And then Webb looks at the first few 100 million years and finds galaxies that the model says should not be there. The tension has a technical name in the cosmological literature. When a specific observation contradicts a model's prediction at a statistically significant but not yet definitive level, it is called a tension. When the evidence becomes overwhelming and undeniable, it becomes a crisis. Right now, the Webb early galaxy observations represent what many researchers describe as a significant tension, not yet a crisis, but heading in that direction as new data continues to accumulate with each new observing cycle. Scientists are appropriately cautious about how they interpret these observations. Some of the most extreme early galaxy candidates found by Webb require follow-up verification before their distances can be confirmed with certainty. A galaxy that appears to be at a certain redshift based on its color profile can sometimes turn out to be a different type of object at a closer distance, mimicking the appearance of something far away. Spectroscopic confirmation, which involves measuring the actual wavelength shifts of specific spectral emission lines rather than relying on color alone, is the gold standard. Webb's near-infrared spectrograph has been conducting spectroscopic follow-ups on many of its candidate early galaxies. In most cases, the high redshift identifications have held up. The galaxies are really there. They are really as distant as they appear. The tension with theory is not an artifact of how we are observing. It is a genuine feature of the early universe. Various proposals have been advanced to explain the observations without abandoning Lambda-CDM entirely. One involves adjusting the properties of dark matter. In the standard model, dark matter is cold, meaning its particles were moving slowly relative to the speed of light when the universe was young. Cold dark matter forms small clumps first, which hierarchically merge into larger structures. This bottom-up assembly is one of the framework's key predictions. Some researchers have proposed warm dark matter instead, whose particles moved faster in the early universe. Warm dark matter would suppress the formation of very small structures, but might allow certain intermediate structures to form differently. However, warm dark matter models generally predict fewer small galaxies than we observe in the local universe, which creates a different set of problems. There is no version of dark matter physics that neatly resolves all observations simultaneously. Another proposal involves modifications to the physics of star formation in the early universe. The first generation of stars, called population 3 stars, formed in clouds of pristine hydrogen and helium with no heavy elements. These stars were likely much more massive than typical stars today, and would have ended their lives in powerful explosions that enriched the surrounding gas with heavy elements quickly. Perhaps in that primordial environment, before the first generation of stellar explosions had enriched and stirred the surrounding gas, star formation could briefly achieve higher efficiencies. Simulations have found some theoretical support for this idea, but they have difficulty reaching the nearly 100% efficiencies that some Webb observations appear to require. The gap between theoretical maximum and observed reality remains uncomfortably wide. A more radical proposal, discussed seriously by some physicists, is that the early universe went through a phase of enhanced gravity, where the gravitational constant was temporarily stronger than it is today. A stronger gravitational force would pull gas together faster, allow more rapid cooling, and enable star formation to proceed more quickly and more completely. Some theoretical frameworks in modified gravity models predict exactly this kind of time-varying gravitational strength, but there is no direct evidence that gravity has changed its strength over cosmic history, and testing such ideas is extraordinarily difficult. Perhaps the most philosophically significant possibility is that the Big Bang was not the beginning, or at least not the kind of beginning we usually imagine. Our standard picture involves the entire observable universe emerging from an infinitely or near infinitely hot, dense state. This is sometimes described as a singularity, but it is important to understand what this actually means. The Big Bang singularity is not a point in space. It is a moment in time. Before that moment, in the standard model, there was no time, no space, no matter. The universe simply began, but our physical theories break down at the singularity. General relativity, our best theory of gravity and space-time, predicts the singularity but cannot describe what happens at it. Quantum mechanics, which governs matter at the smallest scales, is not properly integrated with general relativity at the scales relevant to the very early universe. A complete theory of quantum gravity, which physicists have sought for decades, does not yet exist. In the absence of that complete theory, we cannot say with certainty that the universe had a beginning in any absolute sense. Serious proposals in theoretical physics describe the Big Bang as a transition rather than a creation, a quantum tunneling event from a prior state, a bounce from a previous contracting phase, or one of many Big Bang events in an eternally expanding multiverse. None of these alternatives has the same level of observational support as Lambda-CDM, but the existence of multiple serious theoretical alternatives is itself a reminder that our picture of the cosmos remains incomplete. The history of cosmology is rich with examples of how apparent certainties have been overturned by new data. For most of human history, The universe was assumed to be eternal and unchanging. When Isaac Newton published his laws of gravity in 1687, he recognized the obvious implication. If gravity is universally attractive, why has the universe not collapsed? His answer was effectively theological. Divine intervention must be maintaining the balance. Newton's universe was static, infinite, and supernaturally maintained. Albert Einstein, working 3 centuries later, gave us the mathematical machinery to describe a dynamic universe. When he completed his general theory of relativity in 1915 and applied it to the cosmos as a whole, his equations implied that a universe filled with matter should either be expanding or contracting. A static universe was unstable. To preserve the idea of a static cosmos, Einstein introduced his cosmological constant, a kind of repulsive energy built into the fabric of space-time that would balance gravity and keep the universe stable. He later called this his greatest blunder. The reason he called it a blunder was that the universe was discovered to be expanding after all. Edwin Hubble, working with the Large Telescope at Mount Wilson Observatory in California, demonstrated in 1929 that distant galaxies are moving away from us, and that galaxies farther away are receding faster. This relationship between distance and recession velocity is called Hubble's law. Its existence implied that the universe was once much smaller and denser than it is today, and that running time backward converges everything toward a single state of extreme density and temperature. Georges Lemaitre, a Belgian priest and physicist, had actually proposed this independently in 1927. Before Hubble's observational confirmation, Lemaitre called his idea the hypothesis of the primeval atom. What we now call the Big Bang was his concept. Einstein initially rejected it, reportedly telling Lemaitre that his mathematics was correct, but his physics was abominable. After Hubble's observations, Einstein changed his view. The term Big Bang itself was coined derisively. Fred Hoyle, a brilliant British astrophysicist who advocated for a competing steady-state theory of the universe, used the phrase mockingly in a 1949 radio broadcast, intending it to sound ridiculous. The name stuck. Hoyle's steady-state theory did not. The decisive confirmation that the universe had been hot and dense in the past came in 1965, when radio astronomers Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation entirely by accident. While investigating sources of noise in a communications antenna, the faint glow they detected from every direction in the sky was the afterglow of the Big Bang, predicted theoretically by George Gamow, Ralph Alpher, and Robert Herman in the 1940s. Penzias and Wilson received the Nobel Prize in Physics in 1978 for this discovery. The decades that followed transformed cosmology from a largely qualitative science into a precision discipline. The discovery in the late 1990s that the universe's expansion was accelerating rather than slowing down as gravity should cause earned another Nobel Prize in 2011. 2 independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, were using Type Ia supernova as standard candles to measure the expansion rate at different epochs. Both expected to measure a deceleration. Instead, both found an acceleration. Distant supernovae were dimmer than expected, meaning they were farther away than a decelerating universe would have placed them. The finding was so unexpected that both teams initially suspected systematic errors in their measurements. After years of cross-checking, the conclusion held. The universe is accelerating. Dark energy was the name given to whatever is causing this. It now constitutes approximately 68% of the total energy content of the universe in the Lambda-CDM model. We have no idea what dark energy actually is at a fundamental level. The simplest explanation is Einstein's cosmological constant, reinterpreted as the energy density of empty space itself, the vacuum energy. But the value of that cosmological constant that our particle physics theories predict is wrong by somewhere between 50 and 120 orders of magnitude, depending on the calculation method. This discrepancy between the quantum mechanical prediction of vacuum energy and the cosmologically observed value has been described as the worst prediction in the history of science. Our best theory of particle physics and our best theory of gravity give completely incompatible answers about the energy of empty space. This problem predates Webb and remains unsolved. Dark matter is similarly mysterious. It makes up roughly 27% of the universe's energy budget according to the Lambda-CDM model, but its existence is inferred entirely from its gravitational effects. Galaxies rotate in ways that cannot be explained by the visible mass they contain. Galaxy clusters bend light more strongly than visible mass accounts for. The large-scale structure of the universe formed the way it did because dark matter provided the gravitational scaffolding that ordinary matter fell into. But every dedicated experiment designed to directly detect dark matter particles has come up empty. We know dark matter exists. We know roughly how much of it there is. We do not know what it is made of. So when Webb's observations are discussed, it is worth keeping this broader context in mind. The standard cosmological model is a framework built substantially on things we don't understand. 5% ordinary matter, 27% unknown dark matter, 68% unknown dark energy. And now Webb is telling us that even the ordinary matter we do understand doesn't behave in the early universe the way our models predict. This situation is either deeply uncomfortable or tremendously exciting, depending on your perspective. For most scientists in this field, it is both. There is a second major anomaly in modern cosmology, separate from but potentially related to the Webb observations, that adds to the sense that something is missing from our models. It is called the Hubble tension. The Hubble constant is the number that describes how fast the universe is expanding today. It is measured in units of kilometers per second per megaparsec, meaning for every megaparsec of distance between us and a galaxy, that galaxy is receding at a rate equal to the Hubble constant times 1. Knowing this number precisely is essential for calculating the age and size of the universe and for testing cosmological models. The problem is that there are two primary ways to measure the Hubble constant, and they give different answers. The first method uses the cosmic microwave background. By analyzing the detailed pattern of temperature fluctuations in the microwave background within the Lambda-CDM framework, cosmologists can infer the Hubble constant with high precision. The Planck satellite measurement gives a value of approximately 67 kilometers per second per megaparsec. The second method uses a chain of distance measurements in the local universe called the cosmic distance ladder. Astronomers first measure distances to nearby stars using parallax, the tiny apparent shift in a star's position as Earth orbits the Sun. They use those distances to calibrate the brightnesses of variable stars called Cepheids, which pulsate with a period that depends on their intrinsic luminosity. They use Cepheids to calibrate the peak luminosities of type Ia supernovae in nearby galaxies. They then use type Ia supernovae in distant galaxies to measure the expansion rate directly. This method gives a Hubble constant of approximately 73 kilometers per second per megaparsec. The gap between 67 and 73 sounds modest in percentage terms, about 9%. But both measurements claim very small statistical uncertainties, around 1 to 2%. The discrepancy is therefore roughly 5 standard deviations, well above the threshold conventionally used to declare a discovery in physics. It has persisted for years, despite many careful checks and independent verifications by multiple teams using different methods. The Hubble tension is not explained by any known systematic error in either measurement. Some researchers have proposed that the Hubble tension and the early galaxy problem are related, that both anomalies point toward the same underlying modification of the standard model. If the early universe was different from what Lambda-CDM assumes, that could affect both the apparent Hubble constant inferred from the microwave background and the rate of structure formation that produced early galaxies. The connection is not yet well established, but the possibility is being actively explored. Webb's observations are also revealing new puzzles about how supermassive black holes grew in the early universe. At the center of virtually every large galaxy is a supermassive black hole. Our own Milky Way harbors one with a mass of approximately 4 million times that of the Sun. The largest known supermassive black holes have masses billions of times the mass of the Sun. Today, the mass of a galaxy's central black hole is tightly correlated with the mass of the galaxy's central stellar bulge, suggesting that galaxy growth and black hole growth are deeply linked, regulated by feedback processes in which radiation from the active black hole heats and expels gas from the galaxy, slowing star formation while star formation and gas accretion feed both stellar mass and black hole mass over time. Webb has found early quasars powered by supermassive black holes with masses of hundreds of millions to billions of solar masses, at epochs when the universe was less than 1 billion years old. Explaining how these black holes grew so massive so quickly is itself a significant open problem. The growth of black holes through accretion is limited by a physical boundary called the Eddington limit. When a black hole accretes matter, the radiation pressure from the hot, infalling gas pushes outward. At the Eddington limit, radiation pressure balances gravity and accretion cannot proceed faster. For a black hole to grow from a stellar mass seed to a supermassive black hole within only a few 100 million years requires either accretion that temporarily exceeds the Eddington limit or very massive initial seeds, or both. The clean correlations we observe between black hole mass and galaxy stellar mass in the present-day universe appear to be absent or disrupted in the early universe. Some early galaxies have very massive black holes relative to their stellar mass, suggesting the black hole grew faster than the galaxy's stars. Others appear to have built up stellar mass rapidly without an obviously dominant central black hole. The orderly relationships we see in nearby galaxies may be the end product of a chaotic early history we have only begun to observe. All of these anomalies connect to one of the most fundamental questions in astronomy, the question of first light. The cosmic dark ages lasted from approximately 380,000 years after the Big Bang, when the cosmic microwave background was released, to somewhere between 100 million and 800 million years later, when the first stars and galaxies produced enough ultraviolet radiation to ryanize the surrounding hydrogen. This period, called the Epoch of Rayonization, marks the transition from a dark universe filled with neutral gas to the illuminated universe we see today. Understanding when and how this transition happened is one of Webb's primary scientific goals. The massive early galaxies Webb has found were likely major contributors to rayonization. Their ultraviolet photon output would have helped ionize the surrounding hydrogen, gradually clearing the cosmic fog. But if these galaxies were producing stars as rapidly and efficiently as Webb's observations suggest, the rayonization timeline itself may need to be adjusted. Models that were calibrated to the standard Lambda-CDM galaxy formation history may require revision. Spectroscopy adds another layer to this picture through measurements of metallicity. Astronomers use the word metal to describe any element heavier than hydrogen and helium. Following a long-standing convention, all heavy elements were produced inside stars through nuclear fusion and then dispersed by stellar deaths. The first population 3 stars formed from gas with no metals at all. Only the primordial hydrogen and helium produced in the Big Bang. When those first stars died, they enriched the surrounding gas with metals for the first time. The metallicity of a galaxy is therefore a record of its star formation history. A very young galaxy should have very low metallicity. Webb can measure the metallicities of early galaxies using specific emission lines in their spectra, providing an independent check on their star formation histories. Some early galaxies show lower metallicities than nearby galaxies, consistent with being younger and less chemically evolved. But others show surprisingly elevated metallicities for their apparent age, suggesting they have already processed significant amounts of gas through multiple stellar generations. This is another piece of evidence suggesting that star formation in the early universe proceeded faster than standard models predict. Some theoretical proposals have attempted to address the Webb observations without abandoning Lambda-CDM by invoking a top-heavy initial mass function for early stars. The initial mass function describes the distribution of stellar masses produced in a given star-forming event. In nearby star-forming regions, many low-mass stars are formed for every high-mass star. If the early universe produced proportionally more massive stars, the overall luminosity and feedback characteristics of early galaxies would differ. Massive stars are brighter and shorter-lived than low-mass stars. A top-heavy initial mass function would produce galaxies that appear brighter per unit of stellar mass, which could partially account for the anomalously high luminosities Webb is finding. But it would also produce different chemical enrichment patterns, and it is not clear that all of the observations can be simultaneously explained in this way. Webb is not working alone in this investigation. Radio observatories including the Atacama Large Millimeter Array in Chile and the Very Large Array in New Mexico provide complementary information about the cold gas content and dust properties of early galaxies. X-ray observatories have been searching for signs of active black holes in early galaxy candidates. Gravitational lensing, the bending of light by massive foreground galaxy clusters, is being used to magnify distant background galaxies that would otherwise be too faint to study in detail. The combination of all these observational tools with increasingly sophisticated computational simulations is driving rapid progress. Simulations, like Illustris TNG and Eagle, have succeeded in reproducing many properties of the present-day galaxy population within the Lambda-CDM framework. but they were calibrated to match local observations, and their predictions for the early universe are now being tested against Webb data. The results so far suggest the simulations underpredict the number of massive early galaxies, confirming the observational tension. Next-generation simulations are being developed that incorporate more sophisticated physics, including better treatments of stellar feedback, black hole growth, magnetic fields, and cosmic rays. Some of these simulations are beginning to produce early galaxy populations closer to what Webb observes, but the most extreme objects still resist explanation. The anomalies are also not confined to galaxy masses and star formation efficiencies. They extend to galaxy sizes, which appear to have been more compact in the early universe than expected, and then grew larger over time through mergers. They extend to galaxy colors, which sometimes indicate older stellar populations than should have had time to form. And they include the morphologies of early galaxies, which are often irregular and disturbed, suggesting frequent mergers, but also sometimes surprisingly disk-like or even spiral-like at epochs when our models don't predict such regular structures should exist. That last observation is particularly intriguing. In the Lambda-CDM model, galaxy mergers were extremely common in the early universe, when galaxies were packed more closely together. Mergers are violent, disruptive events that tend to destroy ordered disk structures and create irregular or elliptical galaxies. A galaxy can rebuild a disk over time after a merger, but this takes billions of years. Finding thin, stable disk galaxies in the very early universe, when mergers should have been ubiquitous, is another puzzle that existing models struggle to explain. One of the most underappreciated aspects of the Webb anomalies is what they imply about the cosmic star formation history, the record of how the total rate of star formation across the observable universe has changed over time. Before Webb, surveys had established that star formation peaked roughly 2 to 3 billion years after the Big Bang, a period sometimes called cosmic noon, when the universe was forming stars at a rate roughly 10 times higher than today. Before and after that peak, star formation was lower, earlier because there was less time for matter to collapse and form stars, later because much of the available gas had already been consumed. Webb's observations complicate this picture. The anomalously high star formation rates inferred for some early galaxies, occurring in the first few 100 million years after the Big Bang, suggest that the rise toward cosmic noon began more steeply and earlier than previously thought. Some of the early galaxies Webb has found appear to have been undergoing intense star formation bursts at rates that rival or exceed anything seen at cosmic noon, despite occurring in a universe only a small fraction of its current age. If the universe was forming stars this intensely in its first few 100 million years, a period that was supposed to be dominated by the slow accumulation of matter into the first small structures, then our understanding of how quickly matter organized itself needs significant revision. Webb's infrared capabilities also allow it to see star formation that was previously hidden. Many star-forming regions are enshrouded in dust that absorbs ultraviolet and optical light and re-emits it as infrared radiation. The mid-infrared capabilities of Webb's MIRI instrument are particularly useful for detecting this dust-obscured star formation in early galaxies. Several observational programs using this instrument have found a significant population of dust-shrouded early galaxies that were completely missed by previous surveys. These galaxies were faint invisible light, invisible in the ultraviolet, but revealed by their mid-infrared emission. Including them in the census of early galaxies makes the early universe's star formation rate look even higher than the most anomalous near-infrared observations had suggested. Combining all of these pieces, the near-infrared detections of massive early galaxies, the spectroscopic confirmations of their high redshifts, the mid-infrared detections of their dust-obscured populations, the metallicity measurements suggesting rapid chemical enrichment, and the supermassive black hole mass measurements suggesting rapid black hole growth. A coherent but deeply puzzling picture is emerging. The early universe was more active, more productive, and more structurally complex than our models anticipated. This picture has implications beyond cosmology. One of the fundamental questions in astrobiology is how common planets capable of supporting life actually are. Answering that question requires knowing how quickly heavy elements were dispersed through the universe, because life as we know it requires carbon, oxygen, and other heavy elements that only stars can produce. If star formation and chemical enrichment in the early universe were faster and more efficient than we thought, heavy elements may have been available throughout the cosmos at earlier times than we assumed. This could mean that rocky planets with the chemical ingredients, for life were forming earlier in cosmic history than current models predict. There is a profound connection between the Webb, anomalies, and our own existence. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of calcium in your bones and iron in your blood was made inside a star and scattered into space by that star's death. The atoms in your body were forged in stars that lived and died before the sun was born. The early galaxies Webb is finding in the first few 100 million years after the Big Bang are the direct ancestors of the galaxies we see today. The Milky Way grew in part from structures similar to the ones Webb is now cataloguing. The carbon and oxygen and iron that make life possible trace their origin to stellar generations in those earliest galaxies. When you look at Webb's deep field images, you are in a very real sense looking back at your own origins. The atoms that compose you cross 13 billion years to be here. The development of Webb itself reflects the deeply interconnected nature of scientific progress. The telescope was designed and built by an international collaboration involving NASA, the European Space Agency, and the Canadian Space Agency, with engineers and scientists from more than a dozen countries contributing. Its mirror segments are made from beryllium, chosen for its low thermal expansion and light weight, and coated with a thin layer of gold, chosen for its exceptional reflectivity in the infrared. The detectors were developed specifically for Webb's requirements, pushing the state-of-the-art in infrared sensor technology. The micro-shutter arrays in the spectrograph, those individually controllable microscopic shutters, were a novel invention created specifically for this mission. The entire project cost approximately $10 billion over its multi-decade development timeline, making it one of the most expensive scientific instruments ever built. That investment is already returning extraordinary scientific value. Webb has only been operational since 2022. It has years, potentially decades, of observation ahead of it. The data set will grow substantially, and with it the statistical power to constrain or rule out various explanations for the anomalies it has found. Its observing schedule extends through at least the late 2030s, and early estimates of its propellant budget suggest it may be able to operate for well over 20 years. As the data accumulates, the statistical significance of the early galaxy anomalies will be clarified. If the anomalies are real and systematic, they will grow more significant with time. If they are partly the result of observational biases or small sample sizes, more data will reveal that. The next few years of Webb observations are likely to be decisive in determining whether we are facing a genuine crisis for Lambda-CDM or a tension that can be resolved within the existing framework. Meanwhile, theoretical work continues. The early galaxy observations are motivating a new generation of simulations and analytical models aimed specifically at understanding structure formation in the first billion years of cosmic history. These models are being developed by research groups around the world, tested against Webb data as quickly as it can be published. Different cosmological models make different predictions, not just for galaxy properties, but for the large-scale clustering of early galaxies, the correlation between their properties and their environments, and the statistical distributions of their sizes, morphologies, and star formation rates as a function of redshift. As these predictions are tested against growing Webb data sets, the space of viable explanations will narrow. There are also several new observational tools coming online that will complement what Webb can do. The Square Kilometre Array, currently under construction in South Africa and Australia, will observe the radio emission and absorption from neutral hydrogen across a wide range of redshifts, potentially mapping the structure of the universe through the epoch of reionization and into the cosmic dark ages. Combined with Webb's observations of the first galaxies and quasars, the Square Kilometre Array will help fill in the missing chapter of cosmic history between the microwave background and the earliest structures we can currently detect. Ground-based, extremely large telescopes with mirrors, 30 meters or more in diameter, will be able to perform detailed spectroscopy on early galaxies that even Webb can only barely detect. Space-based missions designed to study dark energy and dark matter through wide-field surveys will measure the expansion history of the universe in much greater detail, potentially revealing whether dark energy has changed over time. Gravitational wave detectors, including LIGO and the planned space-based LISA observatory, will open a gravitational wave window on some of the most energetic events in cosmic history, including the mergers of supermassive black holes. Next-generation cosmic microwave. Background experiments will search for the faint polarization patterns that might reveal the signature of inflationary gravitational waves. Each of these Observational windows provides different and complementary information about the universe's history. The coming decades in observational cosmology are likely to be as scientifically productive as any period in the history of astronomy. The central puzzle remains. Why are the early galaxies Webb is finding bigger, more massive, and more efficiently star-forming than our models predict? What is the universe telling us that we have not yet understood? The history of cosmology suggests two possible ways this could resolve. Sometimes an apparent anomaly dissolves when the data is reanalyzed more carefully. A measurement or analysis method has a subtle systematic error that, once corrected, removes the discrepancy. But sometimes the anomaly is real. When it is, there are two further possibilities. Either it can be explained by adding something to the existing theory, the way Einstein's cosmological constant was eventually reinterpreted as dark energy, or it points to something deeper, requiring a more fundamental revision of our understanding. The discovery of dark energy in the 1990s is actually a useful model for thinking about where cosmology might be heading now. An observation that defied expectation, initially suspected of being systematic error, eventually confirmed beyond doubt, requiring a new component to be added to our picture of the universe, and earning the scientists who made it the Nobel Prize. What that next step looks like in the current situation, nobody knows yet. That is precisely what makes it science rather than dogma. One of the most important things to understand about where we are right now is that Webb is not necessarily demonstrating that our models are wrong in some catastrophic sense. It may be demonstrating that they are incomplete, which is a subtly different thing. Scientific theories are not final truths. They are approximations, more or less accurate, each revealing new layers of complexity and new questions that the previous approximation couldn't even pose. Newton's gravity was a brilliant approximation that explained celestial mechanics with extraordinary precision. Einstein's general relativity revealed it to be an approximation to something deeper. Quantum mechanics revealed the structure of matter in ways classical physics never could. A future theory of quantum gravity will likely reveal something deeper still. Cosmology is following the same trajectory. The Newtonian picture of an eternal static universe was replaced by the Einsteinian picture of an expanding spacetime. The crude initial understanding of an expanding universe was refined into the detailed Lambda-CDM model with its dark matter, dark energy, and inflationary beginning. The tensions and anomalies now accumulating, driven in large part by Webb's observations, may be the early indicators that a further refinement or replacement is needed. Science advances fastest at the boundaries of what it doesn't yet understand. The anomalies in the early universe are exactly that kind of boundary. The question of what we find at that boundary matters beyond the academic world of cosmology. It matters for how we understand our origins. It matters for how we think about what the universe is made of and how it works at the deepest level. It matters for the future of physics, which has been grappling with the incompatibility of general relativity and quantum mechanics for nearly a century. If the Webb anomalies eventually point toward a new understanding of dark matter, or dark energy, or the nature of spacetime itself, the implications could extend far beyond cosmology. Right now, the most honest answer to the question of what Webb has found is this. The early universe contains structures that are more massive, more numerous, more chemically evolved, and more structurally complex than our best theoretical models predict. These structures form too fast, convert gas to stars too efficiently, and enrich themselves with heavy elements too quickly. Some of them even manage to maintain ordered disk shapes in an environment where our models say mergers should be constant and violent. The observations have been checked, cross-verified, and confirmed through spectroscopy. They are not going away. What they mean is still being worked out. The resolution will require more observations, more theoretical work, and possibly fundamental new ideas. It may take years or decades to fully understand, but the search itself, the careful, rigorous, creative work of trying to understand a universe that does not explain itself, is one of the highest expressions of what science is for. If you find these questions compelling, following the ongoing results from James Webb and the theoretical debates they are generating is genuinely worthwhile. The story is far from over. Each new result from deep field observations promises to add another piece to one of the most fascinating puzzles in the history of human knowledge. Webb is currently collecting ancient photons. Some of those photons have been traveling for more than 13 billion years. They carry information about the universe's earliest structures, its first galaxies, its first stars, its first generation of heavy elements. Every photon Webb detects has survived the expansion of space, passed through the telescope's mirror, through filters and diffraction gratings, and registered as a tiny electrical signal on one of its detectors. The fact that we can do this at all is remarkable. The fact that what we find challenges our best theories is not a cause for alarm. It is a sign that the frontier is real and that the work of exploring it matters. There are few more intellectually exciting places to be right now than at the intersection of observational cosmology and fundamental physics, watching Webb's data accumulate and waiting to see what the universe reveals about its own beginning. Whatever comes next, it will build on what Webb has shown us. And what Webb has shown us is that the early universe is not what we thought. That is not a failure. It is an invitation to understand better. And understanding better, one observation at a time, is what science has always been. To fully appreciate the depth of what the James Webb Space Telescope is confronting, it is worth slowing down and carefully unpacking some of the physics that underlies the anomalies it is finding. Each component of the puzzle connects to something fundamental about how the cosmos works at scales that test our understanding to its limits. Let's start with dark matter, because its role in galaxy formation is central to why the Webb observations are so disruptive to our models. Dark matter is not a speculative idea. It is one of the best supported inferences in all of modern physics. The evidence for its existence comes from multiple independent directions. Galaxies rotate in ways that cannot be explained by the gravitational influence of their visible stars and gas. If you plot the rotational velocity of stars in a spiral galaxy as a function of their distance from the center, you expect the velocity to fall off at large distances, where the gravitational influence of the central mass diminishes. Instead, the rotation curves of virtually every spiral galaxy ever measured stay flat or even rise slightly at large radii. Something with additional gravitational influence must be present, distributed through an extended halo surrounding each galaxy. That something is dark matter, galaxy clusters provide a different line of evidence. When light from background galaxies passes close to a massive foreground cluster, gravity bends the light paths, producing distorted and magnified images of the background objects. The amount of this gravitational lensing depends on the total mass of the foreground cluster. In every case where this has been carefully measured, the total mass inferred from lensing far exceeds the mass of the visible gas and stars. Dark matter must make up the difference. The large-scale structure of the universe provides yet another line of evidence. The way galaxies are distributed across cosmic scales, arranged in a cosmic web of filaments, sheets, and voids, matches the predictions of models in which dark matter provides the gravitational scaffolding. Without dark matter, the universe's structure would look very different from what we observe, and the cosmic microwave background itself encodes information about dark matter. The detailed pattern of temperature fluctuations in the microwave background depends sensitively on the ratio of ordinary matter to dark matter and dark energy in the universe. The fit of the Lambda-CDM model to the microwave background is so precise that even small variations in the dark matter density would produce detectable discrepancies. The fit is good. That means the dark matter is there, in roughly the amounts the model requires. What dark matter is not, however, is understood. Decades of experiments designed to directly detect dark matter particles have produced nothing. The most popular candidate for many years was a class of particles called weakly interacting massive particles, or WIMPs. These hypothetical particles would interact with ordinary matter only through gravity and the weak nuclear force, making them essentially invisible except for rare, subtle signals that dedicated detectors might catch. Large underground detectors filled with liquid xenon or other materials have been searching for these signals for years. They have not found them. The parameter space in which WIMPs could hide has been shrinking steadily as detector sensitivity improves, without any detection. Other dark matter candidates include axions, ultralight particles originally proposed to solve a different problem in particle physics. Axions would be much lighter than WIMPs and would behave quite differently on cosmological scales. The search for axions using radio telescope arrays and microwave cavity detectors is ongoing. Then there are primordial black holes. Black holes formed in the early universe before any stars existed, which have also been proposed as dark matter candidates. Gravitational wave observations have constrained this possibility significantly, ruling out primordial black holes of many mass ranges as the dominant form of dark matter. The fact that we cannot directly detect dark matter particles is one of the deepest puzzles in contemporary physics. We know dark matter exists from its gravitational effects. We know it constitutes roughly 27% of the universe's total energy, but we cannot catch it. cannot pin down what it is made of, and cannot explain from first principles why it exists. This foundational uncertainty means that our models of how dark matter halos form and grow, which are central to the Lambda-CDM picture of galaxy formation, may be missing important physics. In the Lambda-CDM model, the formation of dark matter halos is calculated using detailed computational simulations that track how dark matter clumps under gravity over time. These simulations have been run many times, with increasing resolution and sophistication, and they converge on a consistent picture. Dark matter forms a network of halos of different masses, whose statistical properties can be predicted precisely. The galaxies we observe are understood to live inside these halos, with the properties of the galaxies statistically connected to the properties of their host halos. The rate at which halos of different masses form at different cosmic epochs is one of the key predictions of Lambda-CDM. It is precisely this prediction that the Webb observations are straining. When astronomers catalogue all of the galaxies Webb finds at a given epoch and compare the distribution of their masses to what Lambda-CDM predicts for the corresponding dark matter halos, the observed number of massive early galaxies exceeds the theoretical prediction by factors of 10 or more. For the most extreme examples, the most straightforward way to resolve this within the existing framework would be to increase the efficiency with which ordinary matter in those halos is converted to stars. But as we have established, star formation efficiency has physical limits imposed by stellar feedback, and observations suggest some early galaxies are approaching or exceeding those limits. The problem is not just that there are too many massive early galaxies. It is that those galaxies contain too many stars relative to the gas available. Now consider what the first moments after the Big Bang actually looked like, and why the structures we observe must have had their seeds planted incredibly early. In the first fraction of a second after the Big Bang, the universe was unimaginably hot and dense. Temperatures exceeded trillions of degrees, and the fundamental particles of matter, quarks, gluons, leptons, were in a continuous state of creation and annihilation. As the universe expanded and cooled, quarks became bound into protons and neutrons. As it cooled further, protons and neutrons combined to form the nuclei of light elements. This process of primordial nucleosynthesis, occurring in the first few minutes, produced roughly 75% hydrogen, 25% helium, and trace amounts of lithium and deuterium. The precise abundances of these elements are another successful prediction of the Big Bang model, confirmed by observations of the oldest stars and gas clouds in the universe. For the next 380,000 years, the universe remained a hot, dense plasma of electrons and atomic nuclei, opaque to radiation. Then, as the temperature dropped below about 3,000 degrees, electrons combined with nuclei to form neutral atoms for the first time. The universe became transparent, and the photons that had been bouncing around in the hot plasma streamed freely. Those photons are what we detect today as the cosmic microwave background. The tiny temperature variations in that microwave background, 1 part in 100,000, are the imprints of quantum fluctuations from the universe's earliest moments. During a period called inflation, hypothesized to have occurred in the first tiny fraction of a second, the universe is thought to have undergone exponential expansion, driven by the energy of a hypothetical field called the inflaton. This expansion stretched quantum fluctuations to cosmic scales. When inflation ended, those stretched fluctuations became the seeds of all subsequent structure. The idea of inflation was proposed by Alan Guth in 1980, and it solved several long-standing puzzles about the early universe with remarkable elegance. One puzzle was the horizon problem. The cosmic microwave background is extraordinarily uniform in all directions, but regions of the sky that are far apart in angle were, according to pre-inflationary calculations, never in causal contact with each other. How could regions that never exchanged energy or information come to the same temperature so precisely? Inflation explains this by positing that they were all in causal contact before the inflationary expansion stretched them apart. Another puzzle was the flatness problem. The universe appears to be very close to geometrically flat, meaning the total energy density is very close to the critical value that separates a universe that will expand forever from one that will eventually recollapse. But in the absence of some fine-tuning mechanism, a universe that starts even slightly different from flat will diverge rapidly from flatness over time. Inflation solves this by stretching the universe to such an enormous size that any initial curvature is diluted to an imperceptibly small value. A third puzzle was the absence of exotic relics. Some theories of particle physics predict that processes in the very early universe should have produced objects called magnetic monopoles, isolated north or south magnetic poles without a corresponding opposite. These have never been observed. Inflation dilutes their expected abundance to negligibility by stretching the volume of space. Inflation is now a standard component of the cosmological model, but it is not a single theory. It is a family of theories, each with a slightly different inflatum potential and slightly different predictions for observable quantities. The mathematical details of inflation make predictions about the statistical properties of the temperature fluctuations in the cosmic microwave background. Those predictions have been tested and confirmed to high precision, but inflation is not yet fully pinned down. Different inflationary models predict slightly different initial conditions for the distribution of matter after inflation, which eventually affects what kinds of galaxies form and when. If Webb's observations eventually force a significant revision of structure formation models, those revised models may require a different version of inflation, or a different mechanism altogether for generating the initial perturbations that seeded structure. The connection is indirect but real. A puzzle about galaxy masses in the early universe could ripple back to questions about the first fraction of a second after the Big Bang. This cascading effect is one of the most striking features of fundamental discoveries in cosmology. Because the universe's history is a chain of causally connected events, a revision in our understanding of any link in the chain propagates through all the others. The age of the universe, the rate of structure formation, the efficiency of star formation, the abundance of heavy elements, the timeline of reionization, the ultimate fate of the cosmos. All of these are interrelated. Webb's observations are pulling on one thread, and the entire tapestry is responding. Let's talk about what the universe's fate might look like, and why the nature of dark energy is so central to that question. If dark energy is truly a cosmological constant, unchanging over time, the universe will expand forever at an accelerating rate. Over an incomprehensibly long timescale, galaxies beyond our local group will be carried beyond our observable horizon, their light redshifting to undetectable wavelengths. The local group itself, bound by gravity, will eventually merge into a single large elliptical galaxy. Stars will exhaust their nuclear fuel. The most massive stars will explode and collapse into black holes or neutron stars. Less massive stars like the Sun will swell into red giants and then cool into white dwarfs, slowly radiating their remaining heat into space over trillions of years. After all the stars have died, the universe will contain only black holes, neutron stars, white dwarfs, and their cold, dark remnants. Then, over vastly longer timescales, black holes will slowly evaporate by a quantum process called Hawking radiation, first described theoretically by Stephen Hawking in 1974. The radiation is unimaginably faint for large black holes, taking longer than the current age of the universe many times over to cause any significant mass loss. But eventually, given enough time, even supermassive black holes evaporate completely, leaving behind only thermal radiation. The universe approaches a state of maximum entropy and minimum useful energy, sometimes called the heat death. This is the standard prediction for the universe's far future. But the story could be different if dark energy is not constant. If dark energy grows stronger over time, the accelerating expansion of the universe could eventually overcome the binding forces holding together not just galaxy clusters and galaxies, but individual stellar systems, planets, and ultimately even individual atoms. This scenario is called the Big Rip. In this future, the expansion rate grows without limit, and everything in the universe is torn apart in a final catastrophic disassembly. The timing of the Big Rip, if it occurs, depends on the rate at which dark energy strengthens, which is currently unknown. If dark energy weakens over time and eventually reverses sign, gravity might eventually halt the expansion and cause the universe to recollapse in a big crunch. A catastrophic reversal of the Big Bang. Some cyclic cosmological models, including Roger Penrose's conformal cyclic cosmology, propose that the universe bounces through an infinite series of such expansions and contractions, with each Big Bang emerging from the remnants of the previous cycle. Current observations suggest that dark energy is behaving much like a cosmological constant, with no detectable change over the epochs we can observe. But future surveys will probe this more precisely. The Euclid Space Telescope, launched in 2023, and the Vera Rubin Observatory coming online in Chile, will measure the expansion history of the universe in much more detail, potentially revealing whether dark energy has evolved over cosmic time. Every piece of this story connects to every other piece. The nature of dark energy connects to the ultimate fate of the universe. The nature of dark matter connects to how galaxies form and how they distribute themselves across cosmic scales. The physics of inflation connects to the initial conditions that determined all subsequent structure. And sitting at the intersection of all of these questions is the James Webb Space Telescope, sending back data that complicates and enriches our understanding at every frontier. It is also worth stepping back to appreciate the sheer scale of what we are talking about when we describe the universe Webb is studying. A light year is the distance light travels in 1 year, approximately 9.46 trillion kilometers. The nearest star beyond our Sun, Proxima Centauri, is 4.24 light years away. If you could travel at the speed of a commercial aircraft, roughly 900 kilometers per hour, it would take over 5 million years to reach that nearest star. The Milky Way galaxy is approximately 100,000 light years across. The distance from the Milky Way to the nearest large galaxy, Andromeda, is approximately 2.5 million light years. The observable universe has a radius of approximately 46 billion light years and contains more than 2 trillion galaxies. These numbers are not metaphors. They are measurements derived from a century of careful observation and cross-checked by multiple independent methods. The universe really is that large. When Webb observes a galaxy at a redshift of 14, it is observing light from an object that was approximately 2.8 billion light years from us when the light was emitted. Today, due to cosmic expansion, that same object is more than 30 billion light years away. When you account for the full geometry of an expanding universe, the most distant objects Webb has observed were receding from us even as they emitted the light we are now detecting. The universe was already expanding faster than light at cosmological distances. Space itself was stretching. This is a deeply counterintuitive feature of the cosmos. Nothing travels faster than light through space, but there is no restriction on how fast space itself can expand. The galaxies Webb studies at very high redshifts were not themselves moving faster than light. The space between us and them was expanding faster than light can cross it. This is why we can see objects that are currently more than 46 billion light years away in a universe that is only 13.8 billion years old. The light left those objects when they were much closer to us, and it has been in transit ever since while the space between us expanded. Understanding this expansion is why redshift is such a powerful tool. As photons travel through expanding space, their wavelengths stretch in proportion to how much space has expanded. A photon emitted with a wavelength of 100 nanometers in the ultraviolet by a galaxy that existed when the universe was 300 million years old arrives at Webb's detectors with a wavelength of roughly 1,000 to 1,500 nanometers in the near-infrared. This is why Webb's infrared sensitivity is not merely helpful for studying the early universe. It is essential. Previous telescopes, including Hubble, had some infrared capability but were fundamentally limited by the size of their primary mirrors and by the temperature at which they operated. A warm telescope is itself a source of infrared radiation, producing a background glow that overwhelms the faint signals from distant galaxies. Hubble, orbiting relatively close to Earth, cannot be kept cold enough to suppress its own thermal emission at the wavelengths where the most distant galaxies emit most of their light. Webb, orbiting 1.5 million kilometers from Earth at the second Lagrange point, permanently shielded from the Sun and Earth by its multi-layer sunshield, can be kept at temperatures below 50 degrees Kelvin. At those temperatures, its own thermal emission is negligible compared to the astronomical signals it is trying to detect. This combination of larger mirror, colder operating temperature, and more sensitive detectors makes Webb not just incrementally better than what came before. It is categorically different. It can see things that were simply invisible to previous instruments, no matter how long you pointed them at the sky. The populations of early galaxies Webb is finding are not the result of looking harder at things Hubble could have detected. They are genuinely new discoveries that no previous technology could have made. The implications for how we do cosmology are significant. Before Webb, the study of the early universe was necessarily limited to the brightest, most extreme objects, the most luminous quasars, the most massive starburst galaxies, the objects that stood out above the noise even with the instruments available. Webb can detect objects at the same distances that are 100 times fainter. This opens up the statistical study of typical early galaxies for the first time. Instead of just seeing the brightest outliers, We can now see representative populations and compare their statistical properties to theoretical predictions. What those comparisons are revealing is a systematic discrepancy that does not go away when you look at typical objects rather than extreme ones. The excess of massive early galaxies relative to model predictions is not confined to the most spectacular outliers. It extends across the distribution of galaxy masses at high redshift. This makes it harder to dismiss as a selection effect or an artifact of studying unusual objects. The early universe observations are also revealing new insights about the relationship between galaxies and their environments. In the present-day universe, the properties of galaxies depend strongly on their environment. Galaxies in the dense cores of galaxy clusters tend to be old, red, and gas-poor, their star formation having been quenched long ago. Galaxies in lower density environments tend to be younger, bluer, and still actively forming stars. This environmental dependence is a key prediction and confirmation of Lambda-CDM models, which predict that the densest environments, hosting the most massive dark matter halos, should form galaxies earliest and quench them first. Webb is beginning to probe how this environmental dependence played out in the early universe. Early results suggest that the connection between environment and galaxy properties was already in place within the first billion years, with some overdense regions hosting surprisingly mature galaxy populations, even at very high redshifts. This is consistent with the idea that the most massive structures in the universe formed their constituent galaxies earliest, but the speed of this process is again faster than standard models comfortably accommodate. There is also a growing body of evidence from Webb about the morphological evolution of galaxies over cosmic time. In the present-day universe, galaxies come in a variety of shapes: spirals with rotating disks of stars and gas, ellipticals with smooth, featureless distributions of stars, and irregulars with chaotic, asymmetric forms. The Hubble sequence, as this classification is called, has been studied for nearly a century. Webb is revealing that this familiar morphological classification was not always in place. In the early universe, galaxies were generally smaller, more compact, and more irregular than their present-day counterparts. But some of them, unexpectedly, already show the beginnings of disk and even spiral structure at very early times. The formation of stable rotating disk galaxies requires a degree of dynamical settling and orderly gas infall that the Lambda-CDM model predicts should take considerable time in the chaotic, merger-dominated early universe. Finding such structures at redshifts corresponding to only a few 100 million years after the Big Bang is adding another layer to the puzzle. These morphological observations connect to one of the most basic questions about the Milky Way itself. Our galaxy is a large spiral with a central bar, two major spiral arms, and a flat rotating disk of stars and gas. How did it come to have this orderly structure? Cosmological simulations suggest it formed through the accretion of smaller galaxies and gas over billions of years, with the disks slowly assembling after the most violent era of merging had passed. The fact that disk galaxies can apparently form much earlier than models predict is a clue that either the merger history was less violent than we thought, or the disk formation process is more resilient, or something else we haven't fully accounted for. One of the most fascinating threads running through all of these observations is the question of the very first stars, the population 3 stellar generation. The universe's first stars formed from the primordial hydrogen and helium produced in the Big Bang, with no heavier elements at all. The physics of star formation in this metal-free environment was quite different from what governs star formation today. Without heavy elements, gas cannot cool as efficiently, and this changes how it fragments and collapses. Theoretical models predict that population 3 stars would have been extremely massive, potentially hundreds of times the mass of the Sun. They would have burned intensely and briefly, living for only a few million years before ending their lives in powerful supernova explosions, or, for the most massive among them, collapsing directly into black holes without an explosion at all. These first supernovae seeded the surrounding gas with heavy elements for the first time. They also produced enormous amounts of ultraviolet radiation during their short lives, beginning to ionize the surrounding neutral hydrogen. The death of the first generation of stars may have created the seeds of the supermassive black holes we observe at the centers of massive galaxies today. If the most massive population 3 stars collapsed directly into black holes without a supernova, those black holes could have served as the initial seeds that grew through accretion over subsequent billions of years. Direct detection of individual population 3 stars is extremely challenging, because they are expected to have been relatively rare compared to lower mass stars, and they lived and died quickly. But Webb has found some intriguing hints, including a peculiar spectral feature in one very early galaxy that some researchers interpret as a possible signature of extremely massive stars or population 3 candidates. These detections are not yet confirmed, and the interpretation is debated. But if Webb can eventually directly detect population 3 stars or their immediate descendants, it would fill one of the most important gaps in our understanding of cosmic chemical evolution. The transition from the first stars to the first galaxies is itself a poorly understood chapter of cosmic history. In the Standard Model, the first galaxies were assembled from the mergers and accretion of smaller star-forming clumps. The first galaxies were not the organized, rotation-dominated structures we see in the present-day universe. They were chaotic, compact, and intensely star-forming. Webb is beginning to observe this epoch directly for the first time, and what it sees is already challenging some of our expectations about how violent and how efficient this process was. There is something philosophically significant about the fact that we have built an instrument capable of detecting light that was emitted before most of the structures we see in the present-day universe existed. The photons Webb collects from the most distant galaxies were traveling through space before the Sun existed, before the Milky Way had assembled its current form, before the Earth existed, before life existed. They have been crossing the expanding universe for virtually its entire history, carrying information about what conditions were like at the very beginning of the cosmic story. The fact that those conditions do not match what our models predict is not a reason for discouragement. It is a reason for excitement. It means the universe still has things to teach us that we cannot yet anticipate. Every great advance in scientific understanding has been preceded by exactly this kind of productive tension between expectation and observation. Consider the historical precedents. In the early 20th century, the discovery that classical physics could not explain the spectrum of radiation emitted by hot objects led directly to the development of quantum mechanics, one of the most successful physical theories ever constructed. The observation that the orbit of Mercury precessed slightly faster than Newton's gravity predicted led to Einstein's general relativity. The unexpected brightness of distant supernovae led to the discovery of dark energy and a Nobel Prize. In each case, an anomaly that could not be explained within the existing framework led to a deeper and richer understanding of how the universe works. The Webb early galaxy anomalies may be the next entry on that list. They may be pointing toward a modification of how dark matter behaves in the early universe. They may be pointing toward previously unknown physics of star formation in metal-free environments. They may be pointing toward a revision of the timeline of cosmic history, or they may be pointing towards something we have not yet imagined. This is genuinely unknown territory, and that is one of the most intellectually honest and thrilling things that can be said about a scientific problem. The researchers working on these questions represent the best trained and most technically sophisticated scientific community in human history. They have access to computational resources that were unimaginable a generation ago. They are using telescopes that took decades and billions of dollars to build, operating at the frontier of human technological capability. And they are doing what scientists have always done, looking carefully at the evidence, comparing it honestly to what their models predict, and following the data wherever it leads. Some of those researchers are now publicly acknowledging that the data is leading somewhere unexpected. Nobel Prize winners are raising questions about whether our picture of cosmic origins needs fundamental revision. These are not sensational claims. They are careful, precise statements about measurements and models and the gap between them. The gap is real. It is not going away, and working out what it means is one of the most important scientific tasks of our era. When Webb eventually exhausts its supply of station-keeping propellant, sometime in the late 2030s or beyond, according to current estimates, it will stop functioning as a telescope, but it will not stop contributing to science. The data it has collected will be analyzed and reanalyzed for decades. New analytical techniques will be applied to archival observations. Patterns that are not yet apparent will emerge as the data is studied in new ways. The scientific legacy of Webb will extend far beyond its operational lifetime. And before it stops operating, Webb will continue to accumulate data on the early universe. Its observing programs include systematic surveys of multiple deep fields, covering a range of sky areas at various depths, designed to build up statistically powerful samples of early galaxies. As these samples grow, The comparisons with theoretical models will become increasingly constraining. Alternative explanations will either survive or be ruled out by the data. The universe is being interrogated with the most sophisticated instrument humanity has ever pointed at the sky. Its answers are not what we expected. Understanding those answers is now one of the defining challenges of 21st century science. In the end, what the James Webb Space Telescope is doing is what all great scientific instruments do. It is extending the reach of human perception. It is allowing us to ask questions about places and times that no human has ever directly observed. It is revealing a universe that is older, stranger, and more complex than our best current theories capture. And it is doing this with a precision and sensitivity that leaves no room to dismiss what it finds. The early universe, it turns out, was a more fertile and dynamic place than we imagined. Galaxies were building themselves faster and more efficiently than the physics we understand should allow. Heavy elements were being forged and scattered in the first few 100 million years at rates that challenge our models of stellar evolution. Supermassive black holes were growing to enormous masses at speeds that push against the limits of what accretion physics can explain. And somewhere in all of this, the seeds were being planted for everything that came after, for stars and planets, and the chemistry of life. The story of how we came to exist is the story of how the universe went from the pure, hot simplicity of the Big Bang to the complex, cool, structured world we inhabit. Webb is showing us that the first chapters of that story were written faster and more dramatically than we thought. The rest of the story, including the chapters that led to planets and life and telescopes, and the curiosity to point them at the past, played out over billions of years that followed. We are the product of 13.8 billion years of cosmic evolution. We are made of elements that were forged in stars that lived and died before the sun was born. We carry within our bodies the chemical legacy of the universe's earliest stellar generations, the same generations that Webb is now observing for the first time. When we look at Webb's images of the early universe, we are not just looking at distant, ancient objects. We are looking at the origins of the atoms that compose us. That is not a metaphor. It is a precise statement of physical fact. The calcium in your bones was produced by nuclear fusion in stars that existed before the solar system. The iron in your blood was made in supernova explosions that may have occurred within the first billion years of the universe's history. The oxygen you breathe was synthesized in the cores of massive stars and dispersed by their deaths. You are, in the most literal sense, made of stardust. And the stars that made you were part of the same early galaxy formation story that Webb is now revealing. Understanding that story better is not just an academic exercise. It is an act of self-discovery at the grandest possible scale. Every improvement in our understanding of how the early universe assembled its first galaxies is an improvement in our understanding of how we came to be here. Every anomaly Webb discovers, every gap between observation and prediction, is a clue about processes and physics that shape the universe we inhabit. The search for understanding continues. The data accumulates, the models evolve, and somewhere in the ancient light that Webb is collecting, photon by photon, galaxy by galaxy, the universe is telling us something about itself that we have not yet fully understood. That is the promise and the challenge of this extraordinary moment in the history of human knowledge. And if you are paying attention, there is nowhere more interesting to be. If the questions raised in this exploration resonate with you, consider staying engaged with the ongoing results from deep field cosmology. Every few months, new data from Webb and the observatories working alongside it adds another chapter to the story. The results are not always dramatic in a single observation, but cumulatively they are building toward one of the most consequential scientific discoveries in human history. Whether that discovery turns out to be a refinement of Lambda-CDM or a replacement of it, the knowledge gained will be foundational to how we understand the cosmos we live in. Stay curious. The universe rewards it. Let's go deeper into a dimension of this story that often gets overlooked in popular accounts. The precise observational techniques that allow astronomers to extract the information they need from the faint light of ancient galaxies. When Webb detects a galaxy billions of light years away, it is collecting an extraordinarily small number of photons. The faintest galaxies Webb studies might deliver fewer than a handful of photons per second to its detectors across its entire primary mirror. This makes the precision of the measurement challenge very real. Every photon carries information, but the information is incomplete. and extracting reliable science from such sparse data requires sophisticated techniques built on decades of methodological development. The first challenge is simply identifying that a faint smear of light in a deep field image is actually a distant galaxy rather than some other kind of object. Astronomers use color information for an initial classification. Different types of objects have different color signatures, meaning they emit different proportions of light at different wavelengths. A galaxy in the very early universe, whose light has been heavily redshifted, will be completely invisible at short wavelengths and only detectable in the infrared. This characteristic dropout from short wavelength bands is called the Lyman break technique because it exploits a sharp absorption feature in galaxy spectra at a specific wavelength called the Lyman limit. By looking for objects that appear in infrared images but disappear in shorter wavelength images, astronomers can efficiently identify candidate high redshift galaxies. This technique was pioneered in the 1990s and drove much of what Hubble discovered about the early universe. Webb has taken it to a new level of sensitivity, identifying dropout objects at redshifts that would have been completely inaccessible to Hubble. But color-based selection is a screening tool, not a definitive measurement. The actual confirmation of a galaxy's distance requires spectroscopy. Spectroscopy works by dispersing the incoming light from a source across its constituent wavelengths, creating a spectrum. This spectrum is not smooth and featureless. It contains specific narrow emission and absorption features at wavelengths determined by the physics of atoms. Hydrogen, for instance, emits and absorbs light at specific wavelengths corresponding to electronic transitions in its atomic structure. The most important for early galaxy studies is the Lyman alpha emission line, produced when hydrogen atoms transition from their first excited state to their ground state. This line is emitted at a wavelength of 121.6 nanometers in a galaxy's rest frame. For a galaxy at a redshift of 10, this line arrives at Webb's detectors at a wavelength of 1,216 nanometers in the near-infrared, stretched by a factor of 10. By identifying the Lyman alpha emission line and measuring its observed wavelength, astronomers can calculate the galaxy's redshift precisely. This tells them both the look-back time and, using a cosmological model, the distance. Webb's near-infrared spectrograph can simultaneously obtain spectra for up to about 100 objects in its field of view, making it enormously efficient at confirming the redshifts of multiple candidate early galaxies in a single observing session. But spectroscopy with Webb is not just about confirming distances. The spectra of early galaxies contain a wealth of additional information. The widths of emission lines tell astronomers about the velocities of gas within the galaxy, revealing rotation and turbulence. The ratios of different emission lines tell astronomers about the chemical composition of the gas and the nature of the radiation field illuminating it. The presence or absence of absorption features tells astronomers about the history of star formation and chemical enrichment, and the overall shape of the spectrum, called the continuum, tells astronomers about the mix of stellar ages and temperatures contributing to the galaxy's light. From all of this spectral information, astronomers can infer the galaxy's stellar mass, its star formation rate, its gas metallicity, whether it hosts an active black hole, how much dust it contains, and how it compares to galaxies of similar mass in the present-day universe. The fact that all of this information is encoded in the spectrum of a galaxy that emitted its light 13 billion years ago, and that we can extract it from the faint signal that reaches us after that 13 billion year journey, is one of the most remarkable things about modern observational astronomy. The stellar mass estimates for distant galaxies deserve a closer look because this is where some of the most heated debates about the Webb anomalies are focused. Mass estimates for distant galaxies are derived not directly, the way you might weigh an object on a scale, but indirectly, by modeling the light the galaxy emits. The light from a galaxy is the summed emission of all its stars. Stars of different masses, temperatures, and ages emit different amounts and colors of light. A young massive star burns blue and hot, contributing mostly ultraviolet and blue light. An old low-mass star burns red and cool, contributing mostly red and infrared light. A galaxy's overall light output reflects the mix of all these stellar populations, convolved with the effects of dust that absorbs some wavelengths more than others and re-emits them in the infrared. By modeling this complex mix of stellar populations and comparing the model predictions to the observed colors and brightness of a galaxy at multiple wavelengths, astronomers can infer the galaxy's stellar mass, age distribution, and star formation history. This technique is called spectral energy distribution fitting, and it is one of the workhorses of modern galaxy studies. The technique works well for nearby galaxies, where we have detailed information to calibrate against. For very early universe galaxies, the calibrations become less reliable. The stellar populations in those galaxies may be quite different from anything we have studied nearby. The initial mass function, describing the distribution of stellar masses produced when gas fragments into stars, may have been different in the metal-free or low metallicity environments of the early universe. If the stellar population models used to fit early galaxy spectra are even slightly wrong, the inferred stellar masses could be systematically offset from the true values. This is a legitimate source of uncertainty, and astronomers are working hard to quantify it. Comparisons between different stellar population models, tests of the models against well-studied local galaxies in unusual chemical environments, and use of multiple independent observables to constrain galaxy properties simultaneously are all being used to assess the reliability of mass estimates for early universe galaxies. The consensus so far is that while stellar population modeling introduces some scatter and possibly some systematic offset, it is not likely to be wrong by enough to explain the full discrepancy between observed and predicted galaxy masses. The anomalies are probably real, even accounting for modeling uncertainties. There is also the question of contamination from active galactic nuclei. A galaxy that contains a quasar at its center is much brighter than its stars alone would make it. If some of Webb's high redshift candidates are actually quasars, their apparent stellar masses could be overestimated because the light from the accreting black hole is being misidentified as stellar emission, identifying and excluding quasars from galaxy samples. Or correctly modeling the quasar contribution to the light is an important part of the analysis. Webb's spectrograph is very effective at identifying active galactic nuclei because they produce distinctive spectral signatures, including broad emission lines from rapidly moving gas near the black hole. Follow-up spectroscopy has allowed astronomers to identify the quasar-dominated objects and separate them from genuine stellar-dominated galaxies. After this separation, a significant population of genuinely stellar-dominated early galaxies with anomalously high masses remains. The question of gravitational lensing is also relevant. Gravitational lensing, where a massive foreground object magnifies and distorts the image of a more distant background object, can make background galaxies appear brighter and more extended than they would otherwise. This effect can in principle make faint early galaxies detectable that would otherwise be too faint to study. But it also means that apparent fluxes and apparent sizes may be amplified, leading to overestimated masses if the lensing magnification is not correctly accounted for. Astronomers are careful to identify and correct for gravitational lensing in their analyses of early galaxy populations. One of the most powerful tests of the early galaxy mass estimates comes from measuring not just the properties of individual galaxies, but the statistical properties of the entire population. The Lambda-CDM model makes predictions not just about average galaxy properties, but about the full distribution of masses, sizes, luminosities, and other observables as a function of redshift. Comparing the observed distributions to the predicted distributions provides a much more stringent test of the model than comparing single averages. As Webb accumulates more data and the samples of confirmed early galaxies grow, these statistical comparisons will become increasingly powerful. Systematic overestimates of galaxy masses would show up in the distributions in specific ways that could be distinguished from a genuine population excess. If the anomaly is due to modeling errors, the shape of the mass distribution would look different from what a genuine population excess would produce. Early analysis suggests the discrepancy is consistent with a genuine population excess rather than a systematic modeling artifact. But larger samples will provide much firmer ground for this conclusion. The coming years will be important for another reason beyond simply accumulating more early galaxy observations. Webb will increasingly be used to study the large-scale structure of the early universe, not just individual galaxies. The distribution of galaxies in space, how they cluster together, the sizes of the voids between them, and the networks of filaments connecting them collectively encode information about the physics of structure, formation that single galaxy observations cannot provide. The cosmic web in the early universe should look very different from the elaborate, multi-scale structure we see today. In the standard model, early large-scale structure was more uniform, with the cosmic web only beginning to differentiate into its present complex hierarchy. If the early universe was more active and efficient at forming galaxies than we thought, the early cosmic web may show more pronounced structure than our models predict. Observations of protoclusters, groups of galaxies in the process of assembling in the early universe, are one way to probe this. Webb has already found several candidate protoclusters at very high redshifts, and systematic surveys of these structures are among its highest priority observational programs. The intersection of all these observational programs, early galaxy statistics, spectroscopic confirmation, morphological studies, protocluster observations, and metallicity measurements, is building a picture of the early universe that is qualitatively richer than anything we had access to before Webb. That richness is itself scientifically valuable, independent of whether it confirms or challenges our existing models. Even if every anomaly turned out to be explained by refinements within Lambda-CDM, the detailed understanding of early galaxy formation that Webb is providing would represent a major advance. But the anomalies are real, and they are not going away. Each new observing cycle adds more objects to the catalogue of early universe galaxies that are bigger and brighter and more chemically mature than they should be. Each new spectroscopic campaign confirms more of the photometric redshifts and reveals more of the physical properties that make these galaxies puzzling. The evidence is accumulating in one direction. Something happened in the early universe that our models do not fully account for. Whether that something is a modification of dark matter physics, an adjustment to the initial conditions set by inflation, a revision of the star formation physics we have assumed, or something more fundamental and unexpected, the answer will be one of the most significant discoveries in the history of cosmology. And the data that will reveal that answer is being collected right now by a gold-coated mirror floating in the cold silence, 1.5 million kilometers from home, doing the work that thousands of scientists across a dozen countries spent decades imagining. Designing, building, launching, and operating. The universe is not under any obligation to be understandable. It owes us nothing. The fact that it is comprehensible at all, that the same physical laws operating in our laboratories apply to galaxies 13 billion light-years away, that the same spectral lines produced by hydrogen in a discharge tube on Earth are recognizable in the spectrum of the most distant object ever observed, is a profound and not at all obvious fact about reality. Einstein called this the most incomprehensible thing about the universe, that it is comprehensible. Webb is extending that comprehension to cosmic scales and cosmic depths that were previously inaccessible. What it is finding is not comprehensible within our current framework. That is an invitation to build a better framework, one that will be deeper, more complete, and more powerful than what we have now. That is how science works. That is how it has always worked. And that is why the puzzles Webb is revealing are not a failure of cosmology. They are its current growing edge. The universe began in a state of extraordinary simplicity. Everything we can observe around us emerged from that simplicity through billions of years of physical processes operating according to consistent laws. We are the product of that long evolution, and now we are looking back at our own origins and finding that the story is more complicated and more surprising than we imagined. That is not something to be troubled by. It is something to be fascinated by. The story is not finished. The best chapters may still be ahead. There is one more dimension of this story that deserves careful attention. The question of what it actually means for a scientific theory to be in trouble, and how the scientific community navigates that uncertainty. Science is not a collection of established facts. It is a process. Theories are tools for making predictions. When predictions match observations, the theory gains credibility. When they don't, the theory faces scrutiny. But the response to a mismatch between prediction and observation is not immediate abandonment of the theory. It is investigation. The mismatch might be due to an error in the observation. It might be due to an incomplete application of the theory. It might be due to a missing physical process not included in the theory. Only after careful elimination of these alternatives does the mismatch become evidence for something genuinely new. The Lambda-CDM model is in this middle phase right now with respect to the Webb observations. The observations themselves have been checked and cross-verified. The spectroscopic confirmations are solid. The masses inferred from spectral energy distribution fitting are uncertain, but not likely to be wrong by the factors needed to dissolve the anomaly. But the theoretical response is still being worked out. Every possible explanation within the existing framework is being explored. New simulations are being run. New analytical models are being developed. And the data set is growing. This is exactly what scientific communities are supposed to do when confronted with anomalies. The process is not always comfortable or linear. There are debates about methodology. There are disagreements about the significance of the anomalies. There are competing theoretical proposals. Some researchers are more inclined to see the anomalies as genuine evidence for new physics. Others are more cautious, emphasizing the modeling uncertainties and calling for more data before drawing strong conclusions. This diversity of scientific opinion is healthy and productive. It is how the community collectively avoids jumping to premature conclusions in either direction. What would it take to move from a tension to a crisis, from a significant discrepancy to a definitive indication that something genuinely new is required? More data, first and foremost. The current anomalous sample, while significant, is still small enough that systematic errors in the analysis pipeline could in principle account for part of the discrepancy. As the sample grows by factors of 10 and then 100 over Webb's operating lifetime, such systematic errors would either remain constant and be overwhelmed by the growing genuine signal, or would be identified and corrected. If the anomaly persists and strengthens as the sample grows, that will be a powerful argument that it is real. Independent confirmation from other instruments and techniques would also be crucial. If the anomalously massive early galaxies are confirmed by completely different observational approaches, using different wavelengths, different instruments, and different analysis methods, the case for new physics becomes much harder to resist. And theoretical coherence matters too. A modified model that can explain the Webb early galaxy anomalies while also explaining everything else. Lambda-CDM explains would be far more compelling than one that fixes the early galaxy problem at the cost of breaking something else. The history of cosmology is littered with proposed modifications to the standard model that resolved one anomaly while creating several others. The next successful theory of structure formation will need to pass the full suite of observational tests, not just the ones where the current model is struggling. The Hubble tension provides a useful parallel. It has been building for over a decade. Multiple independent measurements using different methods have confirmed it. No known systematic error has been found that could explain it away. And yet no proposed modification of Lambda-CDM has succeeded in resolving it without introducing other problems. The tension is real, and it is growing in significance with each new independent measurement. It may be at an earlier stage of development than what will eventually be recognized as the discovery that forced a fundamental revision of the standard model, or it may still somehow resolve into a systematic error. Science does not guarantee a satisfying resolution on any particular timescale. What is perhaps most remarkable about the current moment in cosmology is how many independent anomalies are accumulating simultaneously. The Hubble tension, the Webb early galaxy problem, the excess of large-scale cosmic structure measured by some weak gravitational lensing surveys, the apparent tension between measurements of the growth rate of cosmic structure and the predictions of Lambda-CDM, the difficulty of explaining the rapid growth of supermassive black holes in the early universe. Each of these individually might be explained away. Together, they paint a picture of a theoretical framework that is under significant observational pressure from multiple directions. This convergence of anomalies is either a coincidence, with each individual tension having its own mundane resolution, or it is a signature of something deeper, a systematic gap between our model and reality that manifests differently in different observational contexts. Resolving which interpretation is correct requires more data, more analysis, and more theoretical work. But the fact that thoughtful, careful cosmologists are increasingly treating the convergence of anomalies as a potential unified signal rather than a collection of unrelated coincidences says something about where the field is heading. The theoretical tools available to address these questions are also improving. Advances in computational power and algorithmic efficiency are enabling cosmological simulations of unprecedented resolution and volume. Machine learning techniques are being applied to the analysis of large observational data sets, identifying patterns and correlations that might not be apparent to traditional analysis methods. Analytical tools based on perturbation theory and effective field theory approaches to large-scale structure are providing complementary constraints on cosmological models without the computational expense of full simulations. The combination of Webb's observational capabilities with these improving theoretical and computational tools means that the field is moving quickly. Papers reporting new early universe observations from Webb appear regularly, and theoretical responses to those observations are not far behind. The scientific community is engaged in an intense and productive dialogue between data and theory that is driving rapid progress. The students and postdocs working on these questions today may be the people who eventually identify the modification to Lambda-CDM that resolves the anomalies, or they may be working on the data sets that eventually make it clear that a more fundamental revision is needed. Either way, they are engaged in scientific work of genuine historical significance. The questions they are addressing are among the oldest and most profound that human curiosity has ever posed. Where did everything come from? How did structure emerge from simplicity? How did the conditions for life come to exist? What is the ultimate fate of the universe? These are not new questions. They are as old as human consciousness. But we are uniquely privileged to be living at a time when we have the tools to address them with real precision, and when the data coming in from those tools is complex and surprising enough to challenge our best current answers. Webb is the flagship expression of that privilege right now. Its images of the early universe are not just data. They are windows into a chapter of cosmic history that no human has ever directly observed before. And the light in those images, stretched and cooled by billions of years of cosmic expansion, is telling us something we do not yet fully understand. That is the most exciting thing that can be said about any scientific investigation. Not that we have the answers, but that we are confronting the right questions with powerful enough tools to get answers that surprise us. The universe, as ever, does not care about our expectations. It simply is what it is. And what it is, as Webb is revealing, is stranger and richer and more complex than our best current models capture. Understanding that complexity better is the work of a generation of scientists that is already underway. The James Webb Space Telescope has given them more material to work with than anyone anticipated. And when those scientists eventually arrive at the deeper understanding that resolves today's anomalies and raises tomorrow's questions, the history of how those anomalies were first discovered will begin here, in the first few years of data from the most powerful astronomical instrument humanity has ever built. The early universe is speaking. We are learning to listen. One final thought worth leaving with. The act of building Webb and pointing it at the early universe is itself a data point about the kind of universe we live in. We are made of atoms forged in ancient stars. Those atoms assembled through billions of years of chemistry and biology into organisms capable of curiosity. And that curiosity eventually produced a civilization capable of launching a 6.5-meter gold-coated mirror into space and pointing it at the universe's infancy. The fact that the universe produced beings capable of investigating its own history is not a trivial observation. It is a deep fact about the nature of the cosmos we inhabit. And what those beings are now discovering, using that mirror and the instruments it feeds, is that the universe's history is more complicated and more surprising than even the most sophisticated minds among us had predicted. That is, when you think about it, exactly what you would hope for. A universe that conformed perfectly to every human expectation would be a universe that offered nothing further to discover. The universe we actually inhabit is richer, stranger, and more interesting than that. And James Webb Space Telescope is our current best tool for finding out just how much richer and stranger it is than we thought. The investigation continues, and that ultimately is the most important thing that can be said. The scientific process that drives cosmology forward is worth appreciating on its own terms. It is not a linear march from ignorance to knowledge. It is a spiral, circling the truth at increasing resolution with each revolution. Each generation of astronomers builds on the work of the last, corrects the errors of the last, and sets up the discoveries of the next. The researchers who built Lambda-CDM built on the work of those who established the Big Bang framework. Those who established the Big Bang built on Hubble's discovery of an expanding universe. Hubble built on decades of spectroscopic work by astronomers whose names are less well known today. And so, the chain extends back through centuries of careful observation and theoretical synthesis. Webb is the most recent link in that chain. It will not be the last. Whatever its observations eventually reveal about the early universe, those revelations will motivate a new generation of instruments and a new generation of theories. The Square Kilometre Array, the next generation of extremely large ground-based telescopes, the proposed future space observatories designed to probe dark energy and dark matter with unprecedented precision, all of these will build on what Webb has started. They will answer some of the questions Webb is raising. They will raise new questions that we cannot yet anticipate. This is the nature of scientific progress. It is not the discovery of final answers. It is the progressive replacement of shallower questions with deeper ones, of less precise measurements with more precise ones, of incomplete models with more complete ones. The horizon of knowledge recedes as we advance toward it, always revealing new territory beyond. The universe is old and vast and strange beyond the reach of easy intuition. We are very young within it, and very small, and we have been asking questions about it for only the briefest fraction of its existence. But in that brief fraction, we have learned to measure it, to model it, to trace its history back to its earliest moments. And now, with Webb, we are finding that even our most recent and most detailed models are incomplete. That is not a reason for humility in the defeated sense. It is a reason for excitement in the exploring sense. The universe has more to teach us than we knew. The tools to learn from it are improving. The community of people dedicated to that learning is large and skilled and motivated. And the questions being asked are the deepest questions anyone has ever asked. What more could science ask for than that?